Welcome to ChemSphere Hub. Today's presentation focuses on one of the most fundamental and powerful concepts in vibrational spectroscopy, hydrogen bonding and its signatures in infrared spectroscopy. Today we will explore how hydrogen bonding affects IR frequencies, peak shapes, molecular interaction, and how IR can be used to identify intermolecular and intramolecular hydrogen bonds in various functional groups. Let's begin with a basic introduction. Hydrogen bonding is a special type of intermolecular attraction between a hydrogen atom bonded to an electronegative atom like oxygen, nitrogen or fluorine and a lone pair on another electronegative atom. In IR spectroscopy, hydrogen bonding has strong influence on vibrational frequencies of hydroxyl group, amino group and sub-CH bonds. This presentation will walk through how these effects appear, how to recognize them, and how they help chemists in molecular identification. Before understanding hydrogen bonding effects, it is important to recall the basics of IR spectroscopy. IR spectroscopy detects the absorption of infrared radiation by molecules, causing vibrational transitions. Different bonds absorb at characteristic frequencies, creating a unique spectral fingerprint. We divide the IR spectrum into functional group regions and fingerprint regions. Hydrogen bonding significantly distorts peak in the functional group region. Hydrogen bonding occurs in two main forms. One is intermolecular hydrogen bonding and the other one is intramolecular hydrogen bonding. The intermolecular hydrogen bonding exists between the separate molecule. However, intramolecular hydrogen bonding exists within the same molecule, often forming stable ring-like structures. Both types strongly influence IR frequencies, but in different ways. Intermolecular hydrogen bonding is often concentrated and temperature dependent. However, intramolecular hydrogen bonding gives more stable and predictable IR signatures. Now we will discuss the characteristics of hydrogen bonding. What makes hydrogen bonding unique? It involves the dipole-dipole interaction and partial sharing of electrons between electronegative atoms. Because of this partial bonding, vibrational frequencies of bonds decreases. These bonds exist between any atom and hydrogen and their vibrational frequencies decreases. Hydrogen bonds are directional, meaning their geometry affects strength. These variations in strength are responsible for the broadness and shifting of peaks in IR. Hydrogen bondings depend upon the electrostatic attraction, direction specific interaction, and it affects the vibrational frequencies as we discussed earlier. How hydrogen bonding affects IR spectrum. Hydrogen bonding affects IR spectra in major three ways. One is frequency shift. The stretching vibration of hydroxyl or amino group moves to lower wave number. So it will affect the spectra. And number two is peak broadening. In this case, hydrogen bonded atoms, like if oxygen is bonded with hydrogen and if nitrogen is bonded with hydrogen, peaks become very broad, sometimes covering hundreds of per centimeter distance. So it results in the broadening of peaks. Increases in intensity. So as the intensity changes and if it is increased, the peaks become stronger due to increased dipole moment during vibration. Altogether, these effects allow us to easily recognize the hydrogen bonding in unknown sample. And now we will discuss the hydroxyl or OH bond stretching region. For alcohols, phenols and water, hydrogen bonding dramatically changes the OH stretching region. In this case, two cases will be discussed. Like if free OH bond is present, free OH stretch will appear as a sharp peak that will be at about 3600 per centimeter. And in case of hydrogen bonded, appear as a broad strong band between 2500 to 3300 per centimeter. Sometimes alcohol show both sharp and broad peaks, indicating the presence of both free and bonded OH groups. This is extremely useful in concentration dependent studies. Now NH stretching region is discussed as the NH stretching frequencies are similarly affected in case of free NH bonds. Stretching frequencies are affected for free primary and secondary amines show sharp peaks near 3300 and 3300 to 3500 per centimeter. And if hydrogen bonding occurs, the peaks broaden and shift to lower frequencies. In amides, hydrogen bonding becomes even stronger, creating very broad NH signals. Now, what is Fermi resonance? In some systems, especially carboxylic acid, a phenomena called Fermi resonance occurs. Here the OH stretching vibration couples with overtone or combination bands. This interaction produces a split or unusually broad peak. Recognizing Fermi resonance is important because it helps to differentiate strongly hydrogen bonded systems, especially dimers. Carboxylic acids form cyclic dimers through very strong hydrogen bonding. As a result, the OH stretch becomes extremely broad, sometimes spanning from 2500 to 3300 per centimeter. The C double bond O stretching frequency shifts from 1750 to 1710 per centimeter due to hydrogen bonding. These two features are diagnostic for carboxylic acids in dimer form. Now we will discuss the alcohols. In alcohols, hydrogen bonding is strongly dependent on concentration. At high concentrations, molecules readily form hydrogen bonding networks, producing a broad OH band. At very low concentrations or in non-polar solvents, alcohols can exhibit a sharp OH peak around 3600 per centimeter, indicating free hydroxyl groups. This dual behavior makes alcohols excellent examples of dynamic hydrogen bonding. Amines also exhibit unique pattern. If we discuss the primary peaks, primary amines, they show two NH stretching peaks. However, secondary amines show only one peak. Hydrogen bonding causes these peaks to broaden significantly. IR spectroscopy can help identify the type of amine and detect intramolecular hydrogen bonding, especially in cyclic or aromatic amines. Now we will discuss the intramolecular hydrogen bonding. Some molecules contain internal hydrogen bonding, forming stable six-membered pseudorings. Intramolecular hydrogen bonding produces sharper peaks, lower frequencies than the free OH stretch. Characteristics narrow signals because the hydrogen bond is locked inside the molecule. The IR peak is not as broad as that of intermolecular hydrogen bonds. Intermolecular hydrogen bonding strongly dependent on concentration and solvent. As more molecules come together, the hydrogen bond network grows, broadening and shifting the OH or NH stretching bands. This type of hydrogen bonding is reversible and changes with temperature, pressure and composition. Now we will discuss the solvent effects. Solvents play a major role in hydrogen bonding behavior. Protic versus aprotic solvents. Protic solvents compete with analyte molecule as they also have hydrogen protons, so they disrupt the hydrogen bonding. and aprotic solvents allow strong intermolecular bonding. For example, alcohol show a sharp OH peak in carbon tetrachloride but a broad peak in water or ethanol. This is due to the hydrogen bonding. Temperature effect. Temperature has a significant effect on hydrogen bonding. Lower temperatures strengthen hydrogen bonds, leading to low stretching frequencies, broader peaks, increased intensity. At higher temperature, hydrogen bonds break, shifting peaks back toward the free OH position. Identification by IR. IR spectroscopy is used as a diagnostic tool to determine whether hydrogen bonding is present. By comparing the positions and shapes of OH, NH and C double bond O peaks, chemists can identify the presence and type of hydrogen bonding, strength of interactions, intermolecular versus intramolecular bonding. This makes IR a powerful structural characterization method. Now we can discuss these all discussions with two common examples which will illustrate the hydrogen bonding behavior. We can take the example of alcohol-water system. In this case, it shows continuous shifts depending on the ratio of alcohol to water. And if we see the already as we discussed, the dimers are formed during the carboxylic acid and carboxylic acid dimers show extremely broad OH peaks and lower C double bond O frequency. Studying these systems help us to understand real world behavior in biomolecules, polymers and solvents. Hydrogen bonding analysis by IR has wide applications in structural elucidation of organic compounds, polymer chemistry as material sciences, pharmaceutical research, biomolecular interactions such as protein folding, material sciences and supramolecular chemistry. By understanding H bond effects, we gain insights into stability, reactivity and molecular architecture. To conclude, hydrogen bonding plays a critical role in shaping IR spectra. Broad OH and NH peaks, frequency shifts and changes in intensity are key indicators of hydrogen bonding. IR spectroscopy allows us to distinguish between free and bonded functional groups and to understand molecular interactions on a deeper level. Thank you for your attention. Please like, share and subscribe ChemSphere Hub.